So in this lab, what we're going to be studying are buffers. We're going to look at how the pH changes in a non-buffered solution, as well as how it changes or doesn't change in a buffered solution. And then we're also going to learn how to prepare a buffer to a specific pH. Now, in order to be able to measure pH, what we're going to be using is a pH probe. And so that's what I have here. It is connected to my LabQuest. And so you can see right now it's being stored in an electrolyte solution. That's because we don't want the probe itself to get dried out, otherwise it will stop working. The other thing I have is I have a prepared buffer solution that has a pH of 4, as well as a prepared buffer solution that has a pH of 10. And so I'm going to use these buffered solutions to calibrate my sensor. Now, the probe itself is not actually detecting pH. What it's detecting is a voltage, and that voltage is coming from the H+ ions. The more H+ ions you have, the lower the pH. And so I need to tell the sensor and the LabQuest, okay, it detects this voltage. That voltage means it has a pH of 4. And then do the same thing with the pH of 10. And so that way I can get both sides of the pH so that it's able to properly detect any pH between 0 and 14. So what I want to do is take my probe out of the electrolyte solution, and just give it a little bit of a rinse here. And then I'm going to put this into the pH of 4. And then on my LabQuest, there is an option to calibrate. So I'm going to select that. And again, what it's detecting is a voltage. So right now it's reading at 2.35. I'm going to let it sit for about 10 to 20 seconds to let it fully equilibrate. Basically, what I'm looking for is that voltage value to stabilize. So that tells me that it's reading an accurate voltage. Okay, so right now it's around 2.38. It's stabilized, it's not changing. So I'm going to type in that, okay, that voltage means a pH of 4. So I type in the 4, I hit keep, and then I want to do the same thing, but now I want to do it with a pH of 10. Now, because a pH of 10 means that I have less H+ ions, right now I'm seeing that voltage decrease because there's not as many ions in solution, so it's not going to have as high a voltage. And again, I want to wait for it to stabilize. So it seems like it's holding pretty steady at 1.11 volts. So I'm going to tell it, okay, that is a pH of 10. Go ahead and I'll hit keep, I'll hit okay. And now it's properly measuring that, okay, this solution has a pH of 10. Now, when I'm not using the pH sensor, I do want to put it back into the electrolyte solution. And then just to keep it upright, because it's a little bit top heavy, I just kind of hang it over here. So now that I have calibrated my pH sensor, now I'm ready to start taking different solutions and seeing what's going to happen when I add a strong acid, hydrochloric acid, or a strong base, sodium hydroxide, and see how the pH changes depending on if my solution is a buffered solution or if it is a non-buffered solution. So now that I have my pH sensor calibrated, now what I want to do is I want to test the pH of non-buffered solutions. Now the non-buffered solutions that I'm going to use is just DI water, nothing else in it, as well as a solution of sodium chloride. Sodium chloride is a neutral salt because it comes from a strong acid and a strong base. So both water and sodium chloride are not buffers. So I should see a pretty dramatic change in the pH as I add the hydrochloric acid and the sodium hydroxide. Now I'm going to be doing this dropwise. I'm going to start with adding 1, then 2, then ultimately 3 drops of hydrochloric acid, seeing how the pH changes from even just adding that 1 extra drop. And then I'm also going to do the same thing with the sodium hydroxide. And then we'll repeat all of this in the second part of the lab with buffered solutions to see if the pH also changes dramatically or if we're able to maintain a more constant pH. So I'm going to use my pH sensor I'm just going to give it a quick rinse here. I don't need to dry it because everything is aqueous, or in this case, this is just pure water. Now, before I add the hydrochloric acid, I do want to get the initial pH. So I'm just going to put the sensor in here, and just like before, just give it 10 to 20 seconds, really just waiting for the pH value to stabilize. And so, let's see. So we should expect a pH close to 7, because again, there's just water in here. There's nothing else in here. And so we're seeing a value of around 7.20, makes sense. Okay, and then what we want to do is we want to take our hydrochloric acid and we just want to add 1 drop. Now, in order to try to be consistent in our drop sizes, you want to hold the pipette completely vertical as opposed to on an angle. It helps to get a more consistent drop size. So that's just something to keep in mind, because we do want to try to keep each drop size consistent. So I'm going to add 1 drop of the hydrochloric acid. And so now we should see a pretty dramatic change in the pH. Again, just letting it kind of stabilize, and it's gone all the way down to around 3.80 just from that 1 drop of hydrochloric acid. So we would record that value, and then we're going to do the same thing, but now we'll add a 2nd drop. Again, giving that a stir. We see that the pH now is going down even further. So now it's reading at about 3.17. And then we'll do our 3rd drop. Again, give that a stir. And now we're down all the way to about 2.92. So again, we started at a pH of around 7.2, and just by adding 3 drops of hydrochloric acid, we've dropped now all the way down to 2.92. So pretty dramatic change here. Now we want to do the same thing, but now we want to do this with sodium hydroxide instead of adding hydrochloric acid. So in this case, we should be expecting the pH to increase. So again, we want to record the initial pH in this beaker. It's certainly possible that it can vary slightly. So we don't just want to use the same initial pH that we had previously. And this one is a little bit different. It's reading at about 7.1 as opposed to 7.2. So we would record that value. Then we're going to add 1 drop of our sodium hydroxide. Again, we want to give it time. If the pH doesn't stabilize, then we just kind of want to keep stirring it a little bit. We do see that it has increased, okay? So now it's getting pretty close to 10, actually. Again, just from that 1 drop. So we would record our value at our 2nd drop of sodium hydroxide. So now we're seeing a value of around 10.2. So still increasing a bit. Let's add our 3rd drop. Go. Now, let's see. Just giving it again a chance to stabilize. We're at 10.9. So again, we see a really dramatic change in the pH when we're adding a strong acid and a strong base to a non-buffered solution. Now, we do want to do the same thing that we did with water, but also with sodium chloride. As I mentioned, sodium chloride is a neutral salt. So we should again see a pretty dramatic change in the pH when we add hydrochloric acid or sodium hydroxide. Now, also just like before, we do want to get the initial pH of the sodium chloride solution before we add any of the hydrochloric acid or the sodium hydroxide. And also just like before, again, because sodium chloride is a neutral salt, we're going to see a pH of around 7. And in fact, it's reading at about 7.1. And then we're going to do the same thing that we did before. We're going to add 1 drop, then 2 drops, then 3 drops of hydrochloric acid and see how the pH changes as a result. So there's our first drop. Just kind of give it a stir, let the pH equilibrate. And we do see that the pH now has changed. So it's decreased now to around 3.5. Second drop. Okay. Now we're seeing a pH of around 3.4. And then we'll do our third drop. Now the pH is around 3.1. So we see the same pattern that we saw with the water. Sodium chloride is not able to buffer against a change in pH. So we'll give this a rinse. See this, do the same thing this time. Again, first getting our initial pH before we add any of the sodium hydroxide, and then adding our various drops. So again, just recording, just making sure that, you know, in this beaker, the pH isn't slightly different. But again, it's not, it's reading at around 7.2. And now we're gonna add our drops. So we'll start with just 1 drop of sodium hydroxide. So the pH is increasing. It's reading at about 9.8. Now we'll add another drop. Now we see an increase to about 10.3 from that second drop. And then lastly, our third drop. And now we're getting a pH all the way up to 10.7. So like I said, it's just like what we saw with the water. Sodium chloride is not an effective buffer. And so even just by adding a small amount, a few drops of the various solutions of the hydrochloric acid and the sodium hydroxide, we do see a really significant change in the pH. Now for the second part of the lab, we want to do the same thing we did in the first part with the water and the sodium chloride, except this time we're going to add hydrochloric acid and sodium hydroxide to buffered solutions. So in this situation, we shouldn't see changes to the pH when we add the strong acid and the strong base. So what I'm going to demonstrate for you is the ammonia ammonium chloride buffer, but then you're also going to have data for the acetic acid sodium acetate buffer. So that buffer is acidic. That buffer is going to have a pH more in the 4.5 range. But we're going to start here with the ammonia ammonium chloride buffer, which is a basic buffer. So we'll see a pH above 7. Now, just like we did previously, we want to get the initial pH before we add any hydrochloric acid or any sodium hydroxide. So I'm getting a reading of around 9.8. So again, this is a basic buffer. So that's why my pH is reading above 7 to start. And then we want to go ahead and add our 1 drop of hydrochloric acid. And I'm still getting a reading of 9.8. So that's, again, the idea here is that we don't see a change in the pH because the hydrochloric acid has something to react with. It has the ammonia, which is going, that's the basic component of this buffer. And that's what's going to allow it to neutralize the hydrochloric acid that I'm adding. So if I add a second drop, again, I really shouldn't see a change in the pH, a significant one. And I don't, it's still reading at 9.8. Finally, a third drop. And it's still reading at 9.8. Okay, so we'll give this a quick rinse, and then we're going to do the same thing, but this time adding the sodium hydroxide. Again, let's get our initial pH before we add anything. So this one's reading a little bit lower, more like 9.6, but again, still in the basic range. So we add our sodium hydroxide. Now in this case, the sodium hydroxide is not reacting with the ammonia. It's reacting with the ammonium chloride because that's the acidic component of the buffer. And so that is what's working to neutralize the added sodium hydroxide. And just like before, we don't see a change in pH. It's staying at 9.6. So I add a second drop. Still no change, still reading at 9.6. And then if I were to add a third drop, again, still reading at 9.6. So again, keep in mind that it's a different component of the buffer that's reacting depending on what I'm adding. If I add a strong acid like hydrochloric acid, then it's the basic component, in this case, the ammonia, that's going to work to neutralize that added hydrochloric acid. If I'm adding sodium hydroxide, then it's the ammonium chloride, the acidic component of my buffer. That's what's going to react with the sodium hydroxide to neutralize and allow us to maintain a consistent pH. Now, for the final part of the lab, we're going to be creating our own buffer to an assigned pH. In this case, I want to make my buffer have a pH of 6.0. So to that end, what I have here is I have a weak acid that's dissolved in water. So I'm just labeling this as HA. It does need to be a weak acid because buffers are always weak acid, weak base, never strong acid or strong base. So I have this dissolved in 150 milliliters. And I'm going to take half of this. I'm going to measure out 75 milliliters. And then I'm going to add it to the second Erlenmeyer flask. And then what I'm going to do is I'm going to be adding sodium hydroxide into this flask to neutralize the weak acid and generate a minus. So then when I'm done, I'll have my two components to my buffer. I'll have the weak acid and its weak base that I can combine to make my buffer. So in order to know that I've neutralized all of the weak acid, I'm going to add an indicator, phenolphthalein. You really just need about 3 drops or so, doesn't take a lot. And then what I'm going to do is I'm going to be slowly adding 0.2 molar sodium hydroxide until I get to a pink color. And so the pink color will signify that I'm at the equivalence point. Now notice that I have the sodium hydroxide in a graduated cylinder as opposed to just measuring it straight from the bottle, because I do need to know about how much sodium hydroxide I've added, as we'll see in a little bit. So if I go ahead and I add a little bit of that sodium hydroxide, we see that pink color, right? But when I swirl it, that pink color goes away. And so what's happening there is that the sodium hydroxide reacts with the indicator, and that is going to be basic, so that pink color appears. But as the sodium hydroxide reacts with the HA and gets converted into A minus, that pink color goes away. When the pink color stops going away, when it just stays pink, that means there is no more HA to react with the sodium hydroxide, and that's how I know that I'm done. So I'm just going to keep adding a little bit at a time, swirling as I go to make sure that it's reacting fully. As the pink color you know, if it starts to linger a little bit longer, that tells me that I'm getting closer to the equivalence point. See, again, it went away, but added quite a bit. So I am going to go a little slower. Oh, we're getting really close. See how it took a little bit for that pink color to go away? So I really only want to add a little bit more. Oh, see, and even just that little bit, right? I mean, ideally we would have gotten more of a pale pink, but we can see now that this pink color is persisting. And so that tells me that all of the HA has reacted. And so now I have my HA in this flask and I have my A minus, the conjugate base, in this flask. Now, as I mentioned, I did want to record how much sodium hydroxide I added. And the reason for that is however much sodium hydroxide I added to this flask, I want to add that much water to this flask so that their volumes are equal. So I added about 24 milliliters of the sodium hydroxide. So I'm going to measure out 24 milliliters of water. Okay. And add that to here. So now I have equal volumes as well of my weak acid and its conjugate base. Now, I mentioned that the assigned pH we want to get to a pH that has a value of 6.0. So I've already done the math to figure out, well, how much HA and how much A minus do I need to add to get to that volume, or sorry, to get to that pH. So in order to get to that pH, I want to add 6.8 milliliters of my weak acid. And then I want to add 43.2 milliliters of the conjugate base. So I'm going to measure that out. Okay. Just going to add that into this beaker here. And then 43.2 milliliters. Okay. So I'm going to add that to this as well. Okay. Give that a little bit of a stir. And so the last thing that's left is for me to use my pH sensor, measure the pH, and see, was I able to get to the pH that I was trying for? A little bit of a rinse. You know, we're pretty close. We're a little bit off. So it's reading at a pH of 6.1. And again, we were trying to get to a pH of 6, but we were pretty close. So again, the idea here is that depending on what assigned pH you were trying to get to, that will change how much of the weak acid versus how much of its conjugate base you mix together. But now I have 50 milliliters of a buffer, which if I were to continue to add strong acid or add strong base, I should see the pH maintain at that 6.1, 6.0 level because I have a buffer, so it'll be able to mitigate any changes in the pH.